In this video, we're going to do some calculations involving probabilistic Landau notation. A number of these calculations will be relatively straightforward, but will prove important facts that we will use later. And some of these will be a little bit trickier, and some of them will relate back to things we've already talked about, for example, the weak law of large numbers. All right, for our first exercise, we are going to consider two sequences, xn and yn, random sequences, all the real numbers, and an and bn, positive deterministic sequences, and we are going to imagine that xn is bounded in probability by an, yn is bounded in probability by bn, and we want to prove two results. One about the sum of xn and yn. We would like to show that the sum, which is a new stochastic sequence, is bounded in probability by the sum of an and bn, and that the product, xn times yn, is bounded in probability by the product of an and bn. And one other piece to note right here is we could actually say that the sum is also bounded in probability by the max of an and bn, if we wanted to. We also have that result. All right, we would like to show that xn plus yn is bounded in probability by an plus bn. We'll engage with this from the definition. Want to show lim as c goes to infinity, supremum over n, probability xn plus yn over an plus bn greater than c equals 0. This is our goal. So we're just going to look at this piece of the statement here. We can say the probability that xn plus yn over an plus bn in absolute value is greater than c. We can write as, well, let's just break it up to start. Using triangle inequality, this is less than or equal to the probability that the absolute value of xn over an plus bn, and an and bn are positive, so we don't really have to worry about keeping them in the absolute value, plus yn over an plus bn is greater than c. So again, let's just look at this, remind ourselves what we did. We took this absolute value, we said that that was less than or equal to, the absolute value of the sum is less than or equal to the sum of the absolute values. So if we have something bigger on the right, then it has only increased, not decreased, probability of being greater than c. And we can say this is actually less than or equal to the probability, this part's a little subtle, that this first term is greater than c over 2, or this second term, yn over an plus bn, is greater than c over 2. So what did we do here? Well, we know for the sum to be greater than c, since these are both non-negative, one of the two is going to have to be greater than c over 2. And again, since an and bn are positive, we have that this is going to be less than or equal to the probability that xn over an is greater than c over 2, or yn over bn is greater than c over 2. And this is going to be less than or equal to, we know that the probability of one thing or the other is less than or equal to the probability of one plus the probability of the other. And we get equality if the two are just disjoint. So this is less than or equal to xn over an greater than c over 2 plus probability yn over bn greater than c over 2. We're going to scroll down a little bit. In fact, we know that for each of these statements, because xn equals big OP an and yn equals big OP bn, we know that the supremum, the limit as c goes to infinity, of the supremum over n of each of these two will converge to 0. Okay, so we can say the limit as c goes to infinity, the supremum over n of the probability xn over an greater than c over 2 plus the probability yn over bn greater than c over 2, this we know is equal to 0. Right, again, because xn is bounded in probability by an, yn is bounded in probability by bn. So this then tells us that 0 is less than or equal to the limit as c goes to infinity, supremum over n, probability xn plus yn over an plus bn is greater than c, which is less than or equal to 0. So that then tells us that this is equal to 0, and that completes the proof. All right, now let's look at xn times yn and show that is bounded in probability by an times bn. So let's engage with the definition. So we want to show that the limit as c goes to infinity, the supremum over n, the probability that xn times yn over an times bn, and again, those are positive, so we don't have to worry about them being in the absolute value if we're a little sloppy. We want to show that this limit is equal to 0. So how do we do that? Again, we're going to engage with this probability statement and then take that supremum and the limit at the end. What are we going to do? We are going to rewrite this. So this probability piece, the probability, the absolute value xn, yn over an, bn greater than c, I'm going to break this up sort of into two things. This is, for now, equal to the probability that xn over an times yn over bn is greater than c. And as we did before, we're going to note that since both of these are non-negative random variables, in order for their product to be greater than c, at least one of the two has to be greater than square root of c. All right, so this is then going to be bounded by less than or equal to the probability that xn over an is greater than square root of c, or yn over bn is greater than square root of c. And again, the probability of one event or another event is less than or equal to the sum of the probabilities of each event. So this is less than or equal to the probability of this first event plus the probability of that second event. And now, again, we remind ourselves, okay, xn equals big OP an, yn equals big OP bn, which means that if we put a supremum on each of these and take the limit as c goes to infinity, it doesn't really matter that this is a square root. As c goes to infinity, square root c will similarly go to infinity. Both of these terms should go to 0. So again, this piece implies that the limit as c goes to infinity, supremum over n, p xn over an greater than square root c plus yn over bn square root c equals 0. Again, we have that the limit of the supremum of the sum of these two pieces is equal to 0. And we have bounded this piece we were interested in by the sum of these two pieces. So if we take a supremum over n and then we take a limit as c goes to infinity, then what we will end up getting is exactly what we saw in the previous part. 0 is less than or equal to the limit as c goes to infinity, the supremum over n, the probability xn yn over an bn greater than c, which, as we just saw here, from this and this bound, is going to be less than or equal to 0, which means that this limit is actually going to be equal to 0, which then completes our proof. For the next exercise, we consider a sequence of random variables xn and a deterministic sequence an. We're going to show that if xn is little opan, so asymptotically smaller than an, then xn is also big opan, asymptotically no larger than an. Intuitively, this totally makes sense, but it's worth, I think, engaging with the definitions of little op and big op to do these calculations. While the statement may seem relatively intuitively straightforward, it's actually a little subtle to show. We're going to use proof by contrapositive. We're going to show that if our sequence cap xn is not big OP-an, then it's not little OP-an. We're going to show this using proof by contrapositive. What that means is we are going to assume that xn is not big OP-an and show that that implies that xn is not little OP-an. So we assume xn is not big OP-an, and what that means is that there exists, that's the there exists symbol, some epsilon greater than 0, such that for every, so for every symbol, c greater than 0, there is some n, which I'll write as a function of c, and this is going to be a natural number, such that, and now we have a probability statement, the probability that xn sub c over a n sub c, the probability that this is greater than c in absolute value is going to be greater than epsilon. So again, this is the opposite of being bounded in probability by an. So we are now going to use this to construct a subsequence of xn that is not little op-an. How do we do this? Well, there are many ways. One thing we could do is we could consider a sequence of c values. So maybe c1 equals 1, c2 equals 2, etc. Just this increasing sequence. And now we know that there is some n1 with probability that xn1 over an1 greater than 1 is greater than epsilon. Similarly, some n2 where this holds probability that xn2 over an2 greater than 2 is greater than epsilon, etc. Now, we need to be a little bit careful because it might be that these indices are not in order. It might be that rather than n1 being less than n2, in fact, n1 is greater than n2. In that case, we could just reorder all of these indices such that they are in order from lowest index to largest. And so I'm going to assume, without loss of generality, that they are in the correct order. Without loss of generality, I'm going to assume n1 is less than n2 is less than, etc. We then note that the subsequence xni over ani does not converge in probability to 0, right? Because there's this sliver of mass of at least size epsilon that's not getting closer to 0. In fact, that's getting further and further away from 0. So this ratio does not converge to 0 in probability. And from there, we can say that, in fact, xn over an thus cannot converge to 0 in probability. And that means that xn is not little op-an. Right? And now our proof by contrapositive is done. since we have shown that if xn is not big OPAN, then xn cannot be little OPAN, then that means if xn is little OPAN, then xn is necessarily big OPAN. For this next exercise, we are going to imagine we have a sequence of random variables on R, and for each of those random variables, the variance, sigma squared n, exists is less than infinity. In this case, we have that xn minus its mean, expectation of xn, is big OP sigma n, where sigma n here is the standard deviation of xn. This is a very useful result, and it's basically telling us the width of the sampling distribution of a random variable is no larger than its standard deviation, and we'll see that in general, the standard deviation is really the correct measure of width of a distribution. This result is actually quite straightforward to show. For ease of notation, we are going to let mu n denote the expectation of xn. And now we can actually look directly at our probability statement. So we are interested in looking at the probability that xn minus mu n over sigma n is greater than c for some arbitrary c, right? And we can directly apply Chebyshev's inequality and say that this is less than or equal to, right, 1 over c squared for any c greater than 0. And this actually directly comes from the fact that if we look at the variance of xn minus mu n over sigma n, that this is just 1 over sigma n squared variance of xn, and that this is equal to 1. Right, so this says that our standardized variable now has variance equal to 1, so we can apply Chebyshev's inequality up here with just variance 1. Right, so if we look at this, this is a bound that does not depend on n, so this bound holds uniformly over every n, and in the limit, as c goes to infinity, the right-hand side of this will go to 0. So that tells us then that the limit, as c goes to infinity, supremum over n, the probability that xn minus mu n over sigma n greater than c, that this is equal to 0. This completes the proof. One other piece that I think is quite interesting from here is if we imagine that we were looking at the sample mean of n IID observations. So let's imagine we have z1 up to zn distributed IID from some distribution f. Now we note that so long as the variance of z under f is less than infinity, then the variance of z bar goes to 0 like 1 over n. And so that means that if we look at z bar, and maybe I should call it z bar n, the sample mean of n IID random variables, minus its expectation, this goes to 0, big OP, like the standard deviation, 1 over the square root of n. So again, this says if the variance of each random variable exists, then the sample mean converges to the population mean at a rate no more slowly than 1 over square root of n. So this looks a lot like the weak law of large numbers, except it's quantitative, right? Except in this case, it's giving us a nice rate. And we'll see that this is not just a bound, this is generally going to be sharp as well. For the final exercise, we are going to imagine that we have a sequence of random variables on R. We are going to imagine that this sequence is going to converge to a point x0, and that it converges to that point at a rate no slower than an. So an will be a positive deterministic sequence. And in addition, we imagine that we have a function that has at least one derivative that exists, and that derivative is uniformly bounded. And we are interested in proving something about the rate at which the function applied to the sequence converges to the function applied to the limit. So let's remind ourselves what we're trying to show. We want to show that the limit as c goes to infinity of the supremum over all n of the probability that f of xn minus f of x naught over an is greater than c is 0. So let's draw a little picture to help remind us of what's going on and think about how we might prove this. So in our picture, we have our function f. We have maybe our value x naught, right? We come up here, we have f of x naught here. And the question now is, if we have a sequence that is converging, a stochastic sequence that is converging in probability to x naught at some rate, or no more slowly than some rate, what does that tell us about what happens when we map that sequence through this function? Right? And the answer is, if we imagine sort of zooming in on this region, what we see is that the function really looks like a line with slope equal to the derivative. And so if we imagine that we are concentrating around x naught with high probability, then once we see where that maps to, right, that means f of our function is going to concentrate around f of x naught, and the difference between how we were concentrating down here and how we're concentrating up here is just going to depend on the slope of this line or the derivative. So if we can bound that derivative, then we can say, okay, up to that multiplicative constant that we know is not shooting off to infinity, the rate of convergence of xn to x naught should really look like the rate of convergence of f of xn to f of x naught. So let's write this out. One fact that we are going to use here is that this is the mean value theorem. F of xn minus f of x naught is equal to, for any xn and x naught, so long as f is differentiable, which we know it is, I'm going to call it f prime of x star n times xn minus x naught. And x star n is some value, we're not going to be totally sure what it is, that lives in the interval between xn and x naught. Now let's just look inside here, and this tells us that f of xn minus f of x naught over an is equal to f prime of x star n times xn minus x naught over an. And this is going to be less than or equal to L, that's the bound on the derivative, times xn minus x naught over an. So this thing is going to be smaller than this. So the probability that this exceeds c will be less than or equal to the probability that this exceeds c. So let's make a little more room. So what does this mean? This means that the limit as c goes to infinity, supremum over n, the probability that fxn minus fx naught divided by an is greater than c, this is less than or equal to the limit as c goes to infinity, supremum over n, probability, well, now we have this L, I'm going to move that over to the other side, xn minus x naught over an is greater than c over L. Right, and just as a reminder, right, I just took this and plugged it in down here and moved the L over to the other side. So here we know that this is going to be 0. right? Why? Because xn minus x naught is big O P A n. Great, we're done. So we've now proven our result. We related this difference between f of xn and f of x naught to the difference between xn and x naught, and we noted that things could only shrink or grow by this factor L. And so that means that if xn converges to x naught at a rate no more slowly than an, then f of xn converges to f of x naught similarly at a rate no slower than an.